y prime or dy over dx. We know that they mean the same thing. I need to differentiate the outer function first, which is 1 over this times that quantity prime. So this is hyperbolic cosine 3x, and this is hyperbolic cosine 3x. If you want to break it down like this, you don't have to. You can write the answer all the way. But I just want to explain. So 1 over hyperbolic cosine 3x. And now when I differentiate this, hyperbolic cosine prime is not minus, but hyperbolic sine of 3x. But since this is not plain x, I have to multiply by the inner function prime. Sine over cosine will be hyperbolic tangent of 3x with a 3 in front. And this is it.
Okay, so we don't have to like convert it into a thing where it's like...
No, please don't. Unless you want to evaluate it. So if I want to evaluate hyperbolic cosine of 3, then I have no choice. I have to use e to the third plus e to negative 3 divided by 2. I don't know if these newer calculators came up with hyperbolic functions. I was never curious to find it. So I don't know. I cannot see hyperbolic functions here in the graphing calculator. So if you found an extension or you downloaded something, just let me know. But I don't know in the calculator where you can just punch in and determine. So, but this I can. So this I can put in the graphing calculator. Where are you guys? I lost you again. Okay, so here I will put 0.5 in front. But that's me. You don't have to do that unless you want to. So e to the third, and then plus e to negative 3. You know me. I love my parentheses. And then you get the answer. But if I don't have to evaluate, of course, I will never change, because then I have to change it back to hyperbolic functions. So we never did that. When we differentiated, we said hyperbolic cosine prime is hyperbolic sine.
Okay, thank you. Okay. I think I was just like getting hung up on that.
That's okay. But you need to know the formula, right? Because otherwise we will not be able to evaluate. Good.
I don't have a specific problem, but logarithmic differentiation, I could use a little more practice with.
Yes, so logarithmic differentiation is very important. For example, in, let's say I want the square root of x to tangent x. So this is the function, and I want to find y prime. I cannot differentiate this function. I have to apply natural log. So natural log y equals tangent times natural, of course, tangent x, times natural log of the square root of x. And now I will apply implicit differentiation. So I have 1 over y times dy over dx. And now I have to differentiate this product. Tangent prime is secant squared times natural log of the square root of x plus tangent x times natural log of the square root of x, which is 1 over the square root of x, times the square root of x prime, which is 1 over 2 the square root of x. So then dy over dx, I will multiply both sides by y, and y is the square root of x raised to tangent x. And now let's see what we have in brackets. This cannot be further simplified, so this is secant squared x times natural log of the square root of x. But here this is nice. 2 times the square root of x times the square root of x is 2x. So I have plus tangent x over 2x. And this is it. So I had to apply natural log first before differentiating implicitly.
Could you move it up a little so I could see the rest of it?
You mean like this?
Sorry, the other way. Move it like down like, with the other paper.
I'm sure it's one of the rules, but why do we have the times 1 over square root x and then the 1 over 2 square root x?
Because this, I need to differentiate natural log. When I differentiate natural log, I have 1 over the function times the function prime. But what is the function?
Okay.
Always, I'm using these props because I think they help. You can just put your finger on it and say, okay, natural log of this is 1 over it, but now I have to differentiate this. How do I differentiate this? Well, it's this. Is that better?
Yeah.
Perfect. Next question.
That was helpful. Thank you.
Thank you. Anything else you would like to go back to? Would you like to choose?
Implicit differentiation?
Yes, this was implicit differentiation.
Oh, I thought this was logarithmic.
Yes, but first it was logarithmic.
Oh, same thing.
Yes, first it was logarithmic, but now from this stage to this stage is implicit. But we can choose another.
I'm sorry for being a little slow, but what's the under the plus sign? What's that on the second line you have on that paper? What's the first thing you wrote?
Here?
Yeah.
So it's if I don't put something here, then I'm not sure whether my students will follow. So I copy this plus always, if it's plus.
Yeah, what comes right after the plus?
It's tangent.
Oh, okay. Thank you.
Sorry about that.
So the original function is included in the answer?
So the derivative is obtained by multiplying both sides by y. And this is y.
Oh, okay.
Because I only want the derivative. I don't want the product of 1 over y times this. So I multiply both sides by y, it disappears from here, but it pops up here.
What if you just kept it as y and didn't change it to square root of x to tangent
We
x?
don't want to say dy over dx equals y times this if we have y. If we don't have y, then we have no choice. But I have y. Y is given to me. Is that okay?
Yeah, I understand now.
Perfect. Okay, do we have anything else, or can I choose a problem?
I have a question.
Yes, I'm ready.
About a problem. I think this is called the linearization.
Yes.
So when you do that, right?
Yes, the linearization is a function which is f of a plus f prime of a times x minus a. So you have to be given a function, and you have to be given x equals a. And what this means is if this is the function, and at point when x is a, I have the equation of the tangent line, which is this. The equation of the tangent line. And it says that if you use the function or use the equation of the tangent line to approximate the function near a, you will not have a huge error. But if you want this point, then you have to find a different equation. If you want this point, then you have to find a different equation. That's all it says.
Yeah, so my question was, I often find myself just setting up like point slope formula, and I was just curious if I should stop doing that. I just do it out of habit.
That is fine, because that's what you are determining, but you're wasting time. But it's fine, and that's how we determined it, of course.
Okay. Yeah, I've back checked, and it's almost always been correct.
That's fine.
Okay.
I have to do that a lot. I have to go back and write and make sure I read correctly, and that's fine. There's nothing wrong with it.
Okay. Thank you.
Thank you.
Is there a step after linearization?
No, you're just, you may be asked to evaluate, to see if you are
evaluated
with
for a certain
yeah,
value.
yeah. You're given a value to use the approximation or linearization. Because this is basically an approximation of this function near A, near this point. Anything else, or you would like me to choose?
Can we do the number 4, 3.10 on the homework?
4 and 3.10 in the homework?
Yeah.
Yes,
Yes,
yes, very good. $3.10.
I'm sorry, it's actually number 6. Number 6 is
Number 6.
Yeah.
No worries. Number 6 in the homework in 3.10. Are you sure? Is that something I assigned? Oh, number 6. Number 6?
Yes.
In 3.10?
Yeah.
The one with the find the linear approximation of the function?
Yes.
Okay. So 6 in 3.10. And the function is g of x, the cube root of 1 plus x, and we're given a equals 0, and use it to approximate the number such and such. Okay. Perfect. So we want to look at the linearization. So the linearization is, as I mentioned, in this case with g, doesn't matter, g of a plus g prime of a x minus a. But this is also the same thing with g of x is approximately g of a plus g prime of a x minus a. That's exactly the same thing. So this is the linear approximation, and this is the linearization. They are identical. Okay, so g of 0 is 1. This is x minus 0, which is x. But now I have to determine this. First, I have to find g prime, and then I have to find g prime of 0. So g of x, in this case, is 1 plus x to 1/3. And when I differentiate this, I get 1/3. I get 1 plus x to 1/3 minus 1, which is negative 2/3. Always remember times the inner function prime, but luckily is 1. So this is the same with 1 over 3 and the cube root of 1 plus x squared. So now when I plug in 0 here, this is all 1. The cube root of 1 is 1, and I get 1/3. So this is 1/3. So the linearization or the approximation of the function is 1 plus x over 3. Okay, so they're asking us to use this to approximate the cube root of 0.95 and the cube root of 1.1. So that's all we need to do. Just replace. So x, so this is 1 plus x. So 1 plus x is 0.95. So 1 plus x equals 0.95. So x equals negative 0.05. 1 plus x equals 1.1. So x equals 0.1. So I will replace x by negative 0.05. So g of negative 0.05, approximately 1 minus 0.05 over 3. And for the other one, when x is 0.1, then I will have 1 plus.
I gotta ask, why did you subtract 1 from 0.95 and 1.1?
So let's analyze this. I'm asked to approximate the cube root of 0.95, but I'm talking about this function. And I'm talking about something close to 0. So when I look at these two, it's obvious to me that x is negative 0.05. It has to be close to 0. This is not the reason why I'm doing that, but they have to ask, whatever they ask me, if this is the function and this is a equals 0, they cannot ask me to use the tangent to approximate at 1.1. It's not close to a. So if they want me to approximate here, then I have to use a different function, a different linear approximation. So whatever they are giving me has to be here. If it's here, something is wrong. And then when I compare the cube root of 1.1 to the cube root of 1 plus x, then I know that x is 0.1. And it has to be here. Does it make sense?
Yes.
Thank you. So then this is 0.1. The other one is approximately 1 minus 0.1 over 3. And it says use it to approximate the numbers such and such. So you have to be careful because once we know that this is the approximation, it says near a equals 0. I can't ever ask you to use the approximation when x is 1 or 5 or 6 or negative 3. I have to tell you that x is close to 0. And it is. 0.1 is close to 0, and negative 0.05 is close to 0. In the other direction, it doesn't matter, but close to 0. Very good question. Thank you. Yes, I didn't finish this. So 1 minus 0.1 divided by 3. 0.9666. And what was the other one? 1 minus 0.05 divided by 3. 0.9833. Is this okay?
Yes, thank you.
And you can always go back. Let me share this. Oh, I lost you. I clicked before I shared. Okay, so you can always go back and check. So we claim that 1 plus 0.1 divided by 3, we claim that this what was it? So it was 1. Careful, I think I wrote, so sorry. So it's plus here, okay? So 0.1 was positive, 0.05 was negative, so this is okay with minus, but this is with plus, because we had 0.1 positive. So please make sure that it's positive there. So I have to redo this calculation. It's positive. 0.1 was positive, but indeed 0.05 was negative. Okay, so let me go back. So 1 plus 0.1 divided by 3 is, so let me correct that, approximately 1.0333. And now we're going to check the cube root of 1.1, just to make sure. I'm just whiting out the other number because it was positive. Okay, so now we make sure that it was 1.1, 1.1. You know me, I prefer the power, but you can take the cube root. So 1 divided by 3, and it has to be very close. And the other one was 1 minus 0.05 divided by 3. And we had the cube root of 0.95 and the power 1/3. Okay, so they are trying to trick us. They're not really giving us x, right? They're telling us, oh, use this to find that, but you have to find, see, it's very close. So, but we need to find x, because they're not telling us. They're telling us approximate, use what you determined to approximate this. But I have to find x. I don't know what x is. And 0.95 is very far away from 0, by the way. And so is 1.1. This line may or may not give a good approximation if I jump that far. Good, very good question. Anything else you would like to go back to?